Good afternoon, everyone. Today we will continue to talk about the linear time invariant systems. So in the last class, we have learned the impulse response, frequency response, and the transfer function of the LTI system. So the impulse response is in the time domain. Step response is also in the time domain. Frequency response is in the frequency domain, which is the Fourier transform of the impulse response. And then the transfer function is the Laplace transform of the impulse response. So today, we will continue to talk about the remaining part of this chapter. So first, let's look at the LTI systems described by differential equations. An important class of continuous time linear time invariant systems consists of systems represented by linear constant coefficients, differential equations, that have the following form. So on the left-hand side, we have the summation of an multiplied by the nth order derivative of yt with respect to t, where n is from 0 to capital N. On the right-hand side, we have the summation of bn multiplied by the nth order derivative of xt with respect to t, where n is from 0 to capital N. Okay? So for practical systems, n is usually larger than n, which means the highest order of y is larger than the highest order of x. Okay. So now let's look at one example here. We have a RLC circuit here, and this behavior of the circuit is described by the second order differential equation. So here we have LC multiplied by the second order derivative of VOT with respect to t plus L over R times dVOT over dt plus VOT equal to VIT. Here VIT is the input of the system. VOT is the output of the system. So may I know what is the order of the highest derivative of VOT here? What is the highest order of the derivative of YT of VOT here? What is the order of it? It is equal to 2, right? So here we have n equal to 2. And what is the order of the highest derivative of VIT? 0, correct. N is equal to 0. So it means that we will have we will have A2. We compare this equation with equation 7.21. What is the value of A2? LC. What is the value of A1? L over R. What is the value of A0? So to obtain the transfer function, we are going to B0, 1. Okay. So now let's proceed. We look at the transfer function of this system. So to obtain the transfer function, we are going to apply the Laplace transform to the differential equation. So if we apply Laplace transform to both sides of the equation 7.21 with all initial conditions set to 0, then we will be able to get the summation of an times y tilde s times s to the power of n with n equal to 1 to capital N equal to the summation of bn times x tilde s times s to the power of n with n equal to 0 to capital N. So here, s to the power of n times x tilde s, it is the Laplace transform of the nth order derivative of xt with respect to t, whereas s to the power of n times y tilde s is the Laplace transform of the nth order derivative of yt with respect to t. Okay, so now if I want to obtain the transfer function of this system, what should I do? So from equation 7.22, I can take out y tilde s on the left-hand side of the equation because y tilde s is independent of n, right? Y tilde s is independent of n, therefore I can take it out. And this is multiplied by the summation from n equal to 0 to capital N of an multiplied by s to the power of n. And on the right-hand side of the equation, I will have x tilde s multiplied by the summation from n equal to 0 to n equal to capital N of bn multiplied by s to the power of n. Okay. So what is the transfer function of this system? So to obtain the transfer function, we know that the transfer function is equal to y tilde s divided by s tilde s. This definition is very important. So now I want to know the ratio between y tilde s and x tilde s. So according to this equation here, I know that ytl.s divided by xtl.s will be equal to the summation from n equal to 0 to n equal to capital M of bm multiplied by s to the power of n divided by the summation from n equal to 0 to capital N of an multiplied by s to the power of n. Is that okay? Okay. So this is the transfer function of a system. So for the transfer function, it has two forms. So we can write the transfer function in this format, which is in 7.23b, or in this format, which is 7.23c. Okay? So in this two format, we have two new constants, which is k and k prime. Okay? So now here it states that k is equal to b0 over a0. Why is that? So if we compare 7.23b with 7.23a, they said that k is equal to b0 over a0. What is the reason for that? What is the reason for that? Okay, so let's do it. So if we use equation 7.23b and we make s tend to 0, here we make s tend to 0, and ftl.s, htl.s will tend to, so if s tends to 0, it means that this term will be equal to 1, right? This term will be 1. 1 multiplied by 1 multiplied by 1 multiplied by 1 multiplied by 1. So it means that the whole term here will be equal to 1. So from equation 7.23b, we know that as s tends to 0, htl.s will tend to k. And then, so this is from equation b, okay? So from equation a, we look at when s tends to 0, what will be the value of htl.s? So for this equation here, as s tends to 0, what will be the value of htl.s? We can see that the numerator will tend to b0, and the denominator will tend to a0. So we will have b0 over a0. And therefore, by comparing equation a with equation b, we know that k is equal to b0 over a0. Does it make sense? So now a similar question. So for equation c here, it says that k prime is equal to bm over an. What is the reason for that? Why we have k prime equal to bm over an? So let's look at equation c. Okay. So now I will make s tends to infinity. So I make s tend to infinity. What will be the value of htl.s? So as s tend to infinity, so we look at this from here. Okay. As s tend to infinity, s plus z1 will tend to, yes, infinity, of course. So it will tend to s, right? Because the value will be dominated by s. So z1 will not affect the final value. So it will be dominated by s, the value of s, which means it will tend to s, right? It will tend to s. How about the second term here? S. And the third term here, also s. How about this term? It means that s to the power of n will be much larger than the value of bm over an times s to the power of n over s to the power of n. And then we compare this to equation. What can we find? We find that k prime is equal to bm over an. Any questions? Any questions? No, let's proceed to the slides. Okay. So here, let's say minus pn are the roots of the denominator polynomial f. HTR.S. What is the name of minus Pn? Minus Pn are called the poles of HTR.S because when S is equal to minus Pn, the transfer function will be equal to infinity. That's why minus Pn is called the pole of the transfer function. Minus Pn are the roots of this equation here. You can see that when S is equal to minus Pn, HTR.S will tend to infinity. Minus Pn are the roots of the denominator. So minus Pn is called the pole of the transfer function. And then what is minus Cn? What is minus Cn? So minus Cn are the roots of the numerator polynomial of HTR.S. It is the roots of this equation here. When S is equal to minus Cn, the transfer function will be equal to 0. Therefore, minus Cn are called the zeros of HTR.S. Okay? So these two definitions are very important. So for a system, in equation 7.23, it is said it has capital N poles and capital M zeros. So here we have capital N poles and capital M zeros, and the difference between N and M is called the pole zero axis. It is usually larger than 0 for practical systems. Any questions so far? If there is no question, let's proceed to talk about the system stability. This is very important. So the stability of the system are actually affected by the values of the poles. So here, let's first look at the Beeble stable systems. Okay. So for Beeble stable systems, all system poles should lie on the left half of the S-plane. What does it mean by saying that poles are lying on the left half of the S-plane? It means that the real part of poles is less than 0. The meaning of the sentence is that the real part of the poles should be negative. If the poles are on the left half of the S-plane, then the impulse response will converge to 0 as t tends to infinity. Okay. Maybe let's discuss about it in details. First, let's recall the definition of the Beeble stable systems. What does it mean by saying Beeble stable? We've learned in the previous lectures. What does it mean by saying Beeble stable? It means that if we have a bounded input, then the system will generate a bounded output, right? So if we have a bounded input, then we will have a bounded output, which means that if the modulus of the input is less than or equal to, maybe it's less than or equal to k, and k is a finite value. K is a finite and positive value. Then the corresponding output, yt, the modulus of yt should be less than or equal to L. So if we have a bounded output, then we should have a bounded, if we have a bounded input, then we should have a bounded output. So if the real part of the poles is less than 0, how can the system be Beeble stable? Okay. So let's discuss about it. Okay. So let's consider a case of Let's consider the inverse Laplace transform of S plus alpha plus j omega. What is the inverse Laplace transform of this term? Okay. What is the inverse Laplace transform of this term here? So it is actually e to the power of minus alpha t multiplied by e to the power of minus j omega t multiplied by ut. Okay. So from this inverse Laplace transform, what can we see here? It means that, so here, what is the pole for this vector here? What is the pole of it? We can see the pole is, what is the pole of this system? Minus alpha minus j omega, right? So we can see that the pole is minus alpha minus j omega, and the real part of the pole determines what? Determines the decay of the impulse response, right? So the real part will determine whether the impulse response will decay or not. Am I correct to say that? So if alpha is larger than 0, it means that the impulse response will decay with time. Is it correct to say that? Is it correct to say that? Is it correct to say that? Okay. So if the real part of pole is less than 0, it means that the impulse response will decay with time. Okay. Why is that? Okay. So let us explain here. So for this term here, this is the impulse response, correct? So if we look at the impulse response, what is the magnitude of this impulse response? The magnitude of it is e to the power of minus alpha t times ut. This is the magnitude of it. So if let's say the real part of pole is less than 0, it means that minus alpha is negative. It means that as t increase, if t is increasing, the e to the power of minus alpha t will decrease. It means that it will decay with time. So the real part of pole will determine whether the impulse response will decay with time or not. Does it make sense? Does it make sense? Makes sense, right? And now let's look at the imaginary part of the poles. So the imaginary part of pole, the imaginary part of pole is corresponding to e to the power of minus j omega t. So of course, it will not affect the magnitude of the impulse response. What does it affect? It will affect oscillations. So it will oscillate with time. So it will affect oscillations. Okay. So now let's look at these two examples here. From these two examples, we can see that the real part of the poles are both equal to minus alpha. And here we have assumed that alpha is positive. Therefore, for these two cases, the real part of the poles are negative, which means the impulse response will decay with time. Because the real part of the poles are negative, therefore the impulse response will decay with time. And we also find that for these two examples here, the magnitude of ht will be less than or equal to e to the power of minus alpha t times ut. Is it correct? So for these two examples here, the magnitude of the impulse response will be less than or equal to e to the power of minus alpha t times ut. Does it make sense? Does it make sense? Because here in the first example, it's quite obvious because itself is e to the power of minus alpha t times ut, right? So it is obvious that it is less than e to the power of minus alpha t times ut. For the second case, we know that the magnitude of sine omega naught t is less than or equal to 1. That's why the second impulse response here, it will also be less than or equal to e to the power of minus alpha t times ut. Okay. So now let's look at the output. Okay. So assume we have a bounded input. Let's look at the output, whether the output will be bounded or not. So we know that the output will be equal to the input convolves with what? Convolves with, the output is equal to the input convolves with ht, correct? Now, it is equal to, according to the definition of the convolution, now I can do the integration, right? The definition of the convolution is that xt convolves with ht is equal to the integration from minus infinity to infinity of x alpha multiplied by ht minus alpha, maybe tau, okay, x tau, ht minus tau, d tau. Okay? So this is the definition of the convolution. So from this equation, I will know that modulus of yt will be equal to the modulus of this convolution here, which is x tau multiplied by ht minus tau d tau. Until this step is okay, right? Until this step is okay. Okay. Now I know that this term will be less than or equal to the integration from minus infinity to infinity of modulus of x tau multiplied by the modulus of ht minus tau d tau. Is this step okay? Is this step okay? Does it make sense? Something. Okay. So let me think about this things. Let me think about how to explain this. Maybe I will explain it later on. You just take it for granted first because I cannot think about a good explanation for now. Okay? So we just take it for granted right now, and later on, if we have time, we can discuss about it. Anyway, it's valid. Okay? So I'm sure it's valid. Okay? So anyway, maybe about the experience. Okay, now I know that this term will be less than or equal to the integration from minus infinity to infinity of modulus of x tau multiplied by the modulus of ht minus tau b tau. Is this step okay? Is this step okay? Does it make sense? Something. Okay. So maybe about the space. Maybe about how to explain this. Maybe I will explain it later on. You just take it for granted first because I cannot think about a good explanation for now. Okay? So we just take it for granted right now, and later on, if we have time, we can discuss about it. Anyway, it's valid. Okay? So I'm sure it's valid. Okay? So anyway, until this step, should be okay. And then we have made the assumption that the input is bounded, right? Which makes the assumption that the input is bounded, which means modulus of xt is less than or equal to k. So it means that this term will be less than or equal to the integration from minus infinity to infinity of k multiplied by the integration of modulus of ht minus tau d tau. Is it okay? And it is less than or equal to the integration from minus infinity to infinity of k multiplied by, we know that modulus of ht is less than this term here. So I'm going to substitute this one in here. Then I will have e to the power of minus alpha d minus tau multiplied by ut minus tau d tau. Does it make sense? Because I know that ht is less than this term here. I use this equation. Okay. Now let's plot ut minus tau. So here tau is a variable and t is a constant, which means the waveform of this one is like this. So this is ut minus tau. Okay. Therefore, do I need to do the integration from minus infinity to infinity? No. So I will do the integration from minus infinity to where? T. And it is equal to k multiplied by e to the power of minus alpha t multiplied by e to the power of alpha tau multiplied by 1 d tau. And let's solve this integration here. It is equal to k multiplied by e to the power of minus alpha t multiplied by the integration of this term. So it is equal to e to the power of alpha tau over alpha with tau from minus infinity to t. And it is equal to k times e to the power of minus alpha t multiplied by e to the power of alpha t. Oh, here is minus e to the power of alpha t minus, when tau is equal to minus infinity, this term will be equal to 0, right? Minus 0 divided by alpha. Okay. And now if I multiply this term with this term, what do I have? E to the power of minus alpha t times e to the power of alpha t is equal to 1. So I will have k over alpha. So it means that when the input is bounded, the output is also less than k over alpha. K and alpha are both finite. So it means that for this system, a bounded input will generate a bounded output, right? So we have proved that the bounded input will generate a bounded output. bounded input will generate a bounded output. Any questions for the people stable systems? So now we see that when the real part of the poles are negative, then the impulse response will tend to 0 as t tends to infinity, and also the system will be people stable, which means a bounded input will generate a bounded output. Okay. So another thing is that here is the S map. So the horizontal axis corresponding to the real part of S, the vertical axis corresponding to the imaginary part of S. So when pole is equal to negative alpha, it means that it is located on the horizontal axis. It is located here. Okay? So we use this cross sign to represent poles. And in the second case, where S is equal to minus alpha plus or minus j omega null, which means for the two poles, the real part is equal to minus alpha, and the imaginary part, one of the pole, the imaginary part is equal to omega null, another one is equal to minus omega null. So you should be able to plot the poles on the pole zero map. Now let's proceed to look at marginally stable. For marginally stable systems, one or more system poles lie on the imaginary axis of the S-plane, and no poles would lie on the right half of the S-plane. The poles on the imaginary axis must be distinct. And in this case, the corresponding impulse response will not blow up or become unbounded, but neither will it converge to 0 as t tends to infinity. So in fact, what does it mean by saying the system is marginally stable? We should have an intuitive understanding. It means that for some bounded inputs, it will generate bounded outputs, but for some bounded inputs, it will generate unbounded outputs. In this case, we call this system marginally stable. So let's look at one example here. So for this system, for example here, let's say the transfer function of the system is 1 over s. Okay. Now if I tell you, so for this system, in the first case, if I tell you xt is equal to ut, what will be the output of the system? If the input for this system is ut, what will be the output? So we know that the output is equal to the inverse Laplace transform of x dr s multiplied by h dr s. What is x dr s? What is the Laplace transform of ut here? Laplace transform of ut is 1 over s, right? So we will have inverse Laplace transform of 1 over s multiplied by 1 over s. So what is the inverse Laplace transform of 1 over s square? Tut. So as t tends to infinity, it will tend to infinity. So it is unbounded, right? So it means that we have a bounded input and unbounded output. Okay. And now we look at the second case. Here, the second case, let us assume that xt is equal to cosine omega naught t multiplied by ut. If I assume the input is cosine omega naught t multiplied by ut, then the input is also bounded, right? It is also bounded. It is between -1 and 1, so it is bounded. So now let's look at the output of the system. So the output will be equal to the inverse Laplace transform of x dr s multiplied by h dr s, which is the inverse Laplace transform. What is the Laplace transform of xt? What is the Laplace transform of xt? What is it? S over s squared plus omega naught squared. And then h dr s is, we are talking about this system here. H dr s is 1 over s, right? So it is the inverse Laplace transform of omega naught over s squared plus omega naught squared multiplied by 1 over omega naught. So the output will be 1 over omega naught multiplied by sine omega naught t multiplied by ut. So now for this case, is the output bounded or unbounded? Is it bounded? Bounded, right? So in this case, it is bounded. So in this case, since the bounded output can generate the bounded input can generate bounded output or unbounded output. So here the system is called marginally stable. Sometimes it's stable, sometimes it's not unstable, so it is called marginally stable. Yeah, so means that if you have a bounded input, the output could be bounded or unbounded. So it's just a name. It means that if it is not stable, it is not unstable. So we call it marginally stable. Okay. So now here, for this case, the transfer function is 1 over s, and therefore the pole is equal to 0. So it is at the origin point here. And then the corresponding impulse response will be equal to the inverse Laplace transform of the transfer function. Therefore, it is unique. It's a unique step function here. Now, in the second system, h dr s is equal to omega naught over s squared plus omega naught squared, where the poles are purely imaginary. It is equal to plus or minus j omega naught, and the corresponding impulse response will be equal to sine omega naught t times ut. So we can see that this impulse response is oscillating all the time. It does not converge to 0 or any value. So is this case clear? Marginally stable is okay. So now let's look at the unstable cases. So for the unstable cases, we have two cases for unstable systems. The first case is that one or more system poles lie on the right half of the S-plane, which means the real part of poles is negative or positive. Positive is larger than 0, and then the corresponding impulse response will blow up. why it will blow up. We've learned just now, we've mentioned the real part of pole will determine whether the impulse response will decay or not. If the real part of the pole is larger than 0, it means that the magnitude will increase with time. Therefore, we say it will blow up. So minus r is larger than 0, it means that if the magnitude will increase with time as t tends to infinity, the magnitude of the impulse response will tend to infinity. So we call it blow up. And then let's look at the examples here. So we assume that alpha is larger than 0, omega naught is larger than 0. In the first case, HTLS is equal to 1 over s minus alpha, which means the pole is equal to alpha. It is located on the positive side of the horizontal axis. And then the corresponding impulse response is equal to e to the power of alpha t times dt, which means as t tends to infinity, ht will also tend to infinity. And then in the second case, HTLS is equal to omega naught over s minus alpha squared plus omega naught squared. In this case, the real part of the poles are also positive, and the poles are equal to alpha plus or minus j omega naught. The corresponding impulse response is equal to e to the power of alpha t times sine omega naught t times dt. You can see it is oscillating and also flowing out as t tends to infinity. Okay. So this is the first case of unstable systems, which means we have poles located on the right half of the S-plane. This is the first case of unstable systems. Now let's look at the second case. If we have one or more repetitive system poles lying on the imaginary axis, then in this case, HT will also blow up or become unbounded as t tends to infinity. Okay. So now let's look at the two examples here. In the first example, HTLS is equal to 1 over s square. So in this case, both poles are equal to 0. So we have repeated poles located here. So when you are plotting the pole 0 map, you have to indicate you have two poles here. And then the corresponding impulse response will be equal to t times dt, which means as t tends to infinity, ht will also tend to infinity. And then in the second case, HTLS is equal to omega naught square over s square plus omega naught square square. The poles, so here we have 4 poles because the order of the denominator is equal to 4. Right? The highest order of the denominator is equal to 4. So we have 4 poles. 2 poles are equal to j omega naught. Another 2 poles are equal to minus j omega naught. Okay. So now let's do the inverse Laplace transform. What is the inverse Laplace transform of HTLS here? Of course, you cannot just tell me the answer here. How can we do the inverse Laplace transform of HTLS here? Can we find it on Laplace transform table? And all right. So let's solve it. So I want to construct expression like this using the expressions that I know. So first, let's calculate the first order derivative of s over s squared plus omega naught squared. So I will calculate the first order derivative of s over s squared plus omega naught squared with respect to s. It is equal to s squared plus omega naught square. And then the derivative of s with respect to s is 1. So it is 1 multiplied by s squared plus omega naught squared. And then minus 2s multiplied by s. So in this case, it is equal to minus s squared plus omega naught squared divided by s squared plus omega naught square. But remember that I want to construct this term here. So omega naught square over s square plus omega naught square, it is equal to the first order derivative of s over s square plus omega naught square. So here I already have this term here. What should I do in order to construct this expression? I should add it by. What should I add? I should add this term. Then if I add them up, then inside this bracket, I will have 2 omega naught square divided by s square plus omega naught square. So in order to obtain this term here, I will need to multiply it by 1 over 2. Am I correct? Correct. So now let's do it. So here I will have the first order derivative of s over s squared plus omega naught squared with respect to s. And then the second term, it is 1 over s squared plus omega naught squared. And the whole term is multiplied by 1 over 2. Now I'm able to do the inverse Laplace transform, right? So now I know that the inverse Laplace transform of omega naught squared over s squared plus omega naught squared square is equal to, what is the inverse Laplace transform of the first term here? It is 1 over 2 multiplied by minus p multiplied by cosine omega naught t multiplied by ut, according to the Laplace transform table. And then for the second term here, it is 1 over 2 multiplied by sine omega naught t multiplied by ut. Multiplied by the first term, the second term I have missed 1 over omega naught, because here it is 1 over omega naught multiplied by omega naught over s squared plus omega naught squared is here. Then it should be consistent with the expression on the lecture notes. Does it make sense? So we have looked at the impact of the poles. Now let's look at the impact of the zeros. So the zeros actually will not affect the stability of the system. So no matter what is the value of the zeros, it does not affect the stability of the system. So what does it affect? It will affect the transient response. And this transient response will disappear as t tends to infinity. Later on, we are going to look at what is the so-called transient response. Okay. So now let's look at this example in order to look at the effects of the zeros. So here we consider a second order system, HTL.S, which has a real zero at s equal to 1 over gamma. Note that when gamma equal to 0, the 0 is located at minus infinity and the numerator of HTL.S is equal to 1. Okay. So here, let's solve this example together. So here we have the transfer function HTL.S. It is equal to 18 multiplied by gamma s plus 1 divided by 40s squared plus 22s plus 1. And then I can write it as 18 multiplied by gamma s plus 1 divided by 20s plus 1 multiplied by 2s plus 1. Okay. And then we've learned how to do the extension of the transfer function. Maybe before I do the extension, I will do the normalization first. Okay. So here I will have 18 over 40 multiplied by gamma s plus 1 divided by s plus 1 over 20 multiplied by s plus 1 over 2. Okay. And then I know that this will be equal to 0.45. 0.45. Is it correct? It will be 0.45. Yes. Okay. Multiplied by gamma s plus 1, s plus 1 over 20, s plus 1 over 2. And I assume that it is equal to a over s plus 1 over 2 plus p over s plus 1 over 2. And how do I solve for the value of a and b? We've learned it in the previous lectures. Right? So a will be equal to 0.45 multiplied by gamma s plus 1 divided by s plus 1 over 2 with s equal to minus 20. Therefore, it is equal to 0.45 multiplied by minus gamma over 20 plus 1 over 1 over 2 minus 1 over 20. And it is actually equal to minus 0.5 gamma plus 1. And then p will be equal to 0.45 multiplied by gamma s plus 1 over s plus 1 over 20 with s equal to 1 over 2. And in this case, p will equal to 0.5 gamma minus 1. And then we will be able to get HTL.S is equal to 0.5 gamma minus 1 over s plus 0.5 minus 0.05 gamma minus 1 over s plus 0.05. Okay, now we can do the inverse Laplace transform of the transfer function, and then we can get HT equal to 0.5 gamma minus 1 times t to the power of minus 0.5 t minus 0.05 gamma minus 1 times t to the power of minus 0.05 t multiplied by ut. And then I'm going to talk about the most important part of this example. So how can I derive the step response from the impulse response? So in order to obtain the step response, I have two solutions. The first solution is that step response. Okay. So method one is that we know yt is equal to xt convolves with ht. The step response is the output when the input is a unit step function, which means ot will be equal to ut convolves with ht. ot is the step response. Okay. ot is the step response. Therefore, OTL.S will be equal to 1 over s multiplied by HTL.S, where HTL.S is the transfer function. So that I know the step response will be equal to the inverse Laplace transform of 1 over s multiplied by HTL.S. So this is one way to calculate the step response. The second way we've learned in the previous lecture. So the second way of calculating the step response is to do the integration from minus infinity to t of h tau d tau. It has been explained in the previous lecture. Okay? So you can choose either way to derive the step response, depends on which way is simpler, but you have to determine by yourself. So here we choose to do the integration. So here I choose to do the integration. I know that OT will be equal to the integration from minus infinity to t of h tau d tau. Therefore, I will substitute the expression of ht here. So I will do the integration from minus infinity to t of 0.5 gamma minus 1 times e to the power of minus 0.5 t minus 0.05 gamma minus 1 times e to the power of minus 0.05 t multiplied by ut and maybe tau multi. Tau. 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 So in this case, do I need to do the integration from minus infinity or not? Do I need to do the integration from minus infinity to t or not? No, right? Because we have the step function, unit step function here. So there is no need to do the integration. But what will happen if t is less than 0? If t is less than 0, what will be the value of OT? If t is less than 0, it means that I'm doing the integration on the negative side of the t-axis. So what will be the result of the integration? 0. So it means that when t is less than 0, OT will be equal to 0. And when t is larger than or equal to 0, I know that OT will be equal to the integration starting from 0, t of 0.5 gamma minus 1 multiplied by e to the power of minus 0.5 tau minus 0.05 gamma minus 1 times e to the power of minus 0.05 tau. And I can remove u tau because it's equal to 1 and 1 tau. Therefore, it is equal to 0.5 gamma minus 1 times e to the power of minus 0.5 tau over minus 0.5 with tau from 0 to t minus 0.05 gamma minus 1 times e to the power of minus 0.05 tau over minus 0.05 with tau from 0 to t. And then it is actually equal to, so if we divide this term by minus 0.5, then I will have tau minus tau plus 2, right? Minus tau plus 2. And then for the denominator here, I will have e to the power of minus 0.5 t and then minus 1. Because when tau is 0, this term will be equal to 1. Okay? And then for the second term, so if I divide this term by minus 0.05, I will have minus gamma plus 20. And then multiply by e to the power of minus 0.05 t minus 1. Okay. So now we can write it as 1 minus gamma times e to the power of 0.5 t. And then minus 20 minus gamma times e to the power of minus 0.05 t. And then what do we have now? So here I will have plus gamma minus 2. And here I will have minus, here is gamma minus 2, and here is minus gamma minus 20. And therefore, I will have 2 minus gamma times e to the power of minus 0.5 t minus 20 minus gamma times e to the power of minus 0.05 t. And then here is minus 2 plus 20, so it is plus 18. And this equation is only valid when t is larger than or equal to 0. When t is less than 0, it will be equal to 0. So how can we describe this behavior? So it means that if we combine these two cases, we can represent OT as UT multiplied by this expression here. So it is 2 minus gamma times e to the power of minus 0.5 t minus 20 minus gamma times e to the power of minus 0.05 t plus 18. So this is how we derive the step response of the system. Okay, so now let's look at the step response in detail. So we look at the first term here. So as t tends to infinity, what will be the value of this first term here? For this term here, if I represent it by 1, so as t tends to infinity, 1 will tend to, as t tends to infinity, 1 will tend to infinity or 1 or 0. As t tends to infinity. Infinity. What will be the value of this term here? 0. So we can, how about the second term? As t tends to infinity, what will be the value of the second term? 18. Okay. So we call this second term 18 the steady state value, which means it does not change with time. So it will always remain here. And for the first term, we call it the transient response because it will disappear as t tends to infinity. So this first term is called the transient response of the system. In fact, the values of the zeros will affect the transient response because we can see what is the value of the system. What is the zero of the system? The zero of the system is minus 1 over gamma. We can see as minus 1 over gamma changes, the transient response will also change. You can see that the values of the zero will affect the transient response. Is that correct? So the value here, the value of the transient response will be affected by the values of the zeros. Okay, so now let's look at the graph here. So we can see that we have set different values for gamma here. So for different values of gamma, we will have different values of zeros. You can see that here the transient response will be different if we change the value of the zeros. So the zeros will not affect the stability of the system. Instead, it will affect the transient response. So this center is important. We know that the values of the poles will affect the stabilities of the system, and the values of the zeros will affect the transient response of the system. And the transient response will disappear as t tends to infinity. The stabilities of the system and the values of the zeros will affect the transient response of the system. And the transient response will disappear as t tends to infinity. No, it just means how it looks like as t is small. We're not talking about the decay. No. Of the transient response, if you look at the waveform when t is small, when t is not that large. So we can see that the waveform of ht will change if we change the values of the zeros. What is the value? Okay, so now let's look at the step response in detail. Now let's look at the step response in detail. So we look at the first term here. Let's look at the step response in detail. Now let's look at the step response in detail. Okay, so now let's look at the step response in detail. Okay, so now let's look at the step response in detail. Now let's look at the step response in detail. So we look at the first term here. We look at the first term. So as t tends to infinity, what will be the value of this first term here? For this term here, if I represent it by 1, so as t tends to infinity, 1 will tend to, as t tends to infinity, 1 will tend to infinity or 1 or 0. As t tends to infinity, what will be the value of this term here? 0. So we can, how about the second term? As t tends to infinity, what will be the value of the second term? Response will be affected. So it just means how it looks like as t is small. We're not talking about the decay. No. Of the transient response, if you look at the waveform when t is small, when t is not that large. So we can see that the waveform of ht will change if we change the values of the zeros. So it means that the values of the zeros will affect the transient response. So now let's proceed to look at the example here. Of course, we still have a lot of things to go through. So we have to quickly. So here the transfer function of the RLC system is shown on the right. Here the transfer function is equal to ypr.s over xpr.s, which is equal to rcs over lcs squared plus rcs plus 1. So by substituting the values of rc and l into this transfer function, we can get this expression here. And now we can find out the roots of the denominator. So the roots of the denominator will be the poles. So the roots of the denominator will be the poles. So for this system, we find that the poles are equal to minus 2000 and minus 500, which means the real part of the poles are negative. What does it mean? It means that the system is unstable or stable. Stable, it is stable, right? With stable, 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 stable. Stable, 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 stable. So we can see that the poles are located on the left half of the S plane, and the 0 is equal to 0 in this case. And then if we do the expansion of the transfer function, which means we can extend HQLS as 2500 over 3 multiplied by 4 over S plus 2000 minus 1 over S plus 500. And then we do the inverse Laplace transform, we can get the impulse response of the system. I'm not going to do it. So it is equal to 2500 over 3 multiplied by 4 times e to the power of minus 2000 t minus e to the power of minus 500 t times dt. And then for this step response, so here, in this case, the step response can also be obtained by doing the integration of the impulse response. Do I need to go to it here? No, right? So it's just about the same way. Just use the method we have done before. And now let's look at the first order system. So for the first order system, the relationship between the input and output is described by the first order differential equation here. So this differential equation is capital T multiplied by dyt over dt plus yt is equal to capital K times xt. So here xt is the system input, yt is the system output, k is the DC gain. Why we call this k the DC gain? So in the equation, when we make all the derivatives equal to 0, when all the derivatives are equal to 0, what do we have? We will have yt equal to capital K times xt. So that's why we call k the DC gain. So here, when we call k the DC gain, we have to make all the derivatives equal to 0. Then we will have yt equal to capital K times xt, and capital K is called the DC gain. So the DC gain can also be obtained by setting s in the transfer function equal to 0. So when s is equal to 0, the transfer function will be equal to the DC gain. Okay. So now to find out the transfer function, we need to apply the Laplace transform on both sides of the equation. So here we assume that all the initial conditions are equal to 0, so that we will have capital T times s times y tilde s plus y tilde s equal to capital K times x tilde s, and then the transfer function will be equal to y tilde s divided by x tilde s. It is equal to k over ts plus 1. We can see that when s is equal to 0, h tilde s is equal to k, and k is the DC gain. And here the pole of the system is minus 1 over capital T. So is the system Hibel stable or not? Is it Hibel stable? Yes, so it is Hibel stable. Okay. So now we look at the impulse response. So if we do the inverse Laplace transform of this term here, the impulse response will be equal to k over capital T times e to the power of minus t over capital T times ut. We can see that the decay rate is 1 over capital T. In fact, we have learned this kind of system in the lab session. It is the envelope detector. So in the discharging process, we have the time constant equal to RC, right? RC is corresponding to the capital T here. You still remember? Never mind. Okay. So let's look at the step response. So the step response, as I have mentioned, we can do the integration of the impulse response. Another way is to do the inverse Laplace transform of 1 over s times h tilde s. So here I'm going to choose another method. Okay. So I'm going to choose another method. So here I'm going to use O equal to the inverse Laplace transform of st multiplied by h tilde s. So it is equal to the inverse Laplace transform of 1 over s multiplied by k over capital Ts plus 1. And then it is equal to a over s plus b over s plus 1 over t. And a will be equal to k over ts plus 1 with s equal to 0. Therefore, a is equal to capital T. b is equal to k over s multiplied by capital T with s equal to minus 1 over capital T. So b is equal to minus k. Therefore, OT will be equal to the inverse Laplace transform of k over s minus k over s plus 1 over capital T. Therefore, it is equal to k multiplied by ut minus k multiplied by e to the power of minus t over capital T multiplied by ut. Okay? This is the second method to calculate the step response of a system. Does it make sense? See that the decay rate by setting s in the transfer function equal to 0. So when s is equal to 0, the transfer function will be equal to the DC gain. 0. When all the derivatives are equal to 0, what do we have? We will have yt equal to capital K times xt. So that's why we call K the DC gain. So here, when we call K the DC gain, we have to make all the derivatives equal to 0. Then we will have yt equal to capital K times xt, and capital K is called the DC gain. So the DC gain can also be obtained by setting s in the transfer function equal to 0. So when s is equal to 0, the transfer function will be equal to the DC gain. Okay. So now To find out the transfer function, we need to apply the Laplace transform on both sides of the equation. So here, we apply the Laplace transform of 1 over s multiplied by a over capital Ts plus 1. And then it is equal to a over s. We can do the integration of the impulse response. Another way is to do the inverse Laplace transform of 1 over s times h tilde s. So here I'm going to choose another method. Okay. So I'm going to choose another method. So here I'm going to use O equal to the inverse Laplace transform of st multiplied by h tilde s. So it is equal to the inverse Laplace transform of 1 over s multiplied by a over capital Ts plus 1. And then it is equal to a over s plus b over s plus 1 over t. And a will be equal to k over ts plus 1 with s equal to 0. Therefore, a is equal to capital K. b is equal to over s multiplied by capital T with s equal to minus 1 over capital T. So b is equal to minus k. Therefore, OT will be equal to the inverse Laplace transform of k over s minus k over s plus 1 over capital T. Therefore, it is equal to k multiplied by ut minus k multiplied by e to the power of minus t over capital T multiplied by ut. Okay? This is the second method to calculate the step response of the system. Does it make sense? Since the time is limited, I will move on first. Okay, so now let's look at the second order system. So in the project, the Butterworth filter is actually a Okay, so now let's look at the second order system. So in the project, the Butterworth filter is actually a second order system, which we are going to do in the next week or next week. So here, the second order system, the relationship between the input and output is described by the second order differential equation. So here, the xt is the system input, yt is the system output, theta is the damping ratio. In fact, theta here will determine the decay rate of the impulse response. Later on, we will see. Theta here will determine the decay rate of the impulse response, and omega n is the undamped natural frequency, which will determine the oscillation frequency. And capital K is the DC gain. So here, if we do the Laplace transform to this second order differential equation, we are able to get this equation here, and then we can obtain h tilde s by using y tilde s divided by h tilde s, and it is equal to k multiplied by omega n squared over s squared plus 2 theta times omega n s plus omega n squared. So this is the standard form of a second order system. So here, the pose of the system is equal to minus omega n times theta plus or minus omega n times theta squared minus square root of theta squared minus 1. Okay, so here again, for the second order system, the DC gain will also be equal to h tilde s with s equal to 0. So if you set s equal to 0, then h tilde s will be equal to k omega n squared over omega n squared. So it is still equal to k, right? So when you are required to calculate the DC gain, you just set s in the h tilde s equal to 0. Then you will be obtaining the DC gain. Okay. So now let's quickly move on. So we have different set s in the h tilde s equal to 0. Then you will be obtaining the DC gain. So now let's quickly move on. So we have different kinds of second order system. So first, let's look at the first kind, which means the damping ratio is larger than 0. So when the damping ratio is larger than 0, the pulse of the system will be equal to minus omega n times theta plus or minus omega n times square root of theta squared minus 1. Okay, so here we have theta larger than 1. What can you observe from these two poles? What can you observe from these two poles? Are they real and distinct? Yes, right. They are real and distinct. They are real and distinct. Oh. So we can find that they are real and distinct, right? They are real and distinct. And another thing is that we know that if we compare theta squared minus 1 with theta, which one is larger? Square root of theta minus 1 and theta, which one is larger? Theta is larger, right? Theta is definitely larger, right? So theta is larger, which means the two poles are positive or negative. Positive or negative? Negative. So both poles are real and negative. If both poles are real and negative, is the system Bibo stable or not? Is it Bibo stable? It's Bibo stable. Okay, and when theta is larger than 1, it is called overdamped. And then because the poles are real and distinct, what does it mean? The poles are real and distinct. I've mentioned that the real part of the poles will determine whether the impulse response will decay or not. And the imaginary part of the poles will determine the oscillations, right? So since it only has the real part, it means that there is no oscillation. Only decay will happen. Or not decay. So only decay will, but since the system is Bibo stable, so it will decay. So it means that in this case, there will be decay and no oscillations. There will be decay and no oscillations. And now let's look at the second case. When theta is equal to 1, then the two poles will be equal to minus omega n. So it means that the two poles are both real and negative. So is the system Bibo stable or not? Bibo stable. So there will be decay because the real part is less than 0. So will there be any oscillations? No oscillations because there is no imaginary part. Okay. Now let's look at the third case, underdamped. So in this case, theta is between 0 and 1. Therefore, the two poles are equal to minus omega n times theta plus or minus j omega n times square root of 1 minus theta squared. So we can see that in this case, the poles are a complex conjugate pair, and the real part is negative or positive. Negative. So we can see that the real part of poles is less than 0. So is the system Bibo stable or not? Bibo stable. Okay. And do we have oscillations? Do we have oscillations? Yes, because we have imaginary part. We have imaginary part, so there will be oscillations, and the real part is negative, so there will be decay. So we will have both decay and oscillations. And now in the last case, when theta is equal to 0, it is called undamped. So here, the poles will be equal to plus or minus j omega n, means that the two poles are located on the imaginary axis, right? So we will have the two poles located on the imaginary axis, and the two poles are distinct. So does it mean the system is stable or unstable or marginally stable? Marginally stable. So it is marginally stable. Marginally stable. And since there is no real part, and there will only be imaginary part, since the real part of the poles is equal to 0, so do we have decay or not? No decay, right? No decay. Because the real part is 0, so no decay at all. No decay. But do we have oscillations? Yes, we have oscillations. Now we have summarized all the cases. So when you look at these cases one by one, you will find it is actually simple. Okay? So now let's look at the first case. Now we have summarized all the cases. So when you look at these cases one by one, you will find it is actually simple. Okay? So now let's look at the first case, overdamped system, which means the damping ratio is larger than 1. So as we have mentioned, the two poles are both negative. Right? The two poles are both negative and real. So it means that we will have decay in the impulse response, and we do not have oscillations. We have these rows. So we have decay plus no oscillations. Okay? And now let's look at P1 and P2. We care about the values of P1 and P2, which means the values of the because minus P1 and minus P2 are the poles. The real part of the poles will determine the decay rate. So we do care about the values of P1 and P2. Let's look at them one by one. Okay? So we look at P1 first. P1 is equal to omega n times theta plus omega n times square root of theta square minus 1. We know that theta is larger than 1. So this term will be definitely larger than omega n, which means the first term here will decay at a faster decay rate, and the decay rate is larger than omega n. And then let's look at the second term, P2. So P2 will be equal to omega n times theta minus omega n times square root of theta square minus 1. Actually, from this expression, it is hard to tell whether it is larger than omega n or less than omega n. So therefore, we are going to write it in another form. So it is equal to omega n multiplied by theta and 1 minus square root of 1 minus theta square, or 1 minus 1 over theta square. Is that okay? Until this step is okay. Does it make sense? Okay. Now, it is equal to omega n multiplied by theta. I'm going to write it. So it is equal to omega n multiplied by theta. And in the denominator, I write it as 1 plus 1 minus 1 over theta square. And in the numerator, I will have 1 minus 1 minus 1 over theta square. I think it's this. Okay. And now I have omega n times theta. In the numerator, what do I have? Numerator, I will have 1 over theta square. And in the denominator, I will have 1 plus 1 square root of 1 minus 1 over theta square. And then I will have omega n multiplied by 1 over theta multiplied by 1 over 1 plus square root of 1 minus 1 over theta square. So is this term larger than omega n or less than omega n? We know that theta is larger than 1, and this term is also larger than 1. So the whole term will be less than omega n. So it is less than omega n, which means for this term, the decay rate is larger than omega n. For this term, the decay rate is less than omega n, which means the first term decays faster. The second term decays slower, right? So it means the first term decays faster, the second term decays slower. So if I look at the impulse response, the sum of these two terms will be dominated by the second term. It will be dominated by the second term because the second term decays slower. So at the same time, it will have a larger value, right? So the second term, it will dominate, which means overall the decay rate is less than omega n. Does it make sense? So overall, I will think the decay rate is less than omega n because the sum will be dominated by the second term. Okay? And then I can also calculate the step response. I'm not going to repeat it here because I have done it before. So here you can use the inverse Laplace transform of 1 over s times h squared by s. I can give you the answers for it. I write it before. Here I can do the expansion of the transfer function. And this is actually the OT, is actually the inverse Laplace transform of k over s minus k1 over t1 times s over s plus t1 minus k2 over t2 times s plus t2. And inside this bracket, this is the extension of 1 over s times h squared by s. Now can I move on? 1 over s times h squared by s. And inside this bracket, this is the extension of 1 over s times h squared by s. Now can I move on? So here we calculate the step response using this formula. If you have any questions regarding the extension of the transfer function, you can ask me after the class because we do not have a lot of time today. So I'm going to move on to the next case, which is the critically damped system. So for the critically damped system, the damping ratio will be equal to 1. So here we have repeated real poles. So since the poles are repeated and real and negative, so here we only have the decay and no oscillations in the impulse response. Right? So we have decay but no oscillations. We can see ht is not oscillating at all. It will decay with increasing value of t. And now if we do the inverse Laplace transform of the transfer function, we can see that the impulse response is equal to k multiplied by omega n squared times t to the power of minus omega n t times dt. And then the step response OG, it can also be obtained by using the inverse Laplace transform of 1 over s times h squared by s. And here, this is actually the inverse Laplace transform of k over s minus k over s plus omega n minus k omega n over s plus omega n squared. Okay. Now we compare this case with the previous case. So here, what is the decay rate of the impulse response here? So here the decay rate is equal to omega n. Right? We can see that it is e to the power of minus omega n. So the decay rate is equal to omega n. Compared to the overdamped system, is it decaying faster or slower? Is it decaying faster or slower? Slower or faster? If it is faster, please raise up your hand. Oh, if it is faster, please raise up your hand. Yeah, it's correct. So it is actually decaying faster because, as I have mentioned before, in the overdamped system, ht will be dominated by the second term. So the second term, the decay rate of the second term is less than omega n, which means it is slower than omega n. Therefore, the critical damped system is the fastest, has the highest decay rate. So we can see that it decays faster than over damped systems. Of course, we must have the same omega n. If we have the same omega n, then it is faster than the overdamped system. So now we proceed to look at the underdamped system. For underdamped system, we have conjugate complex poles with damping ratio between 0 and 1. So when we see the poles are complex values, we will know that we will have both decay and oscillations, which is consistent with the phenomenon here. You can see the impulse response is decaying and oscillating, right? So we have decay and oscillations. We have decay plus oscillations. That it decays previous case. So here this is the extension of 1 over s times h. It's actually the inverse Laplace transform of k over s minus k1 over t1 times s over s plus t1 minus k2 over t2 times s plus t2. And inside this bracket, this is the extension of 1 over s times h squared by s. Now can I move on? So here we calculate the step response using this formula. If you have any questions regarding the extension of the transfer function, you can ask me after the class, because we do not have a lot of time today. So I'm going to move on to the next case, which is the critically damped system. So for the critically damped system, the damping ratio will be equal to 1. So here we have repeated real poles. So since the poles are repeated and real and negative, so here we only have the decay and no oscillations in the impulse response. Right? So we have decay but no oscillations. We can see ht is not oscillating at all. It will decay with increasing value of t. And now if we do the inverse Laplace transform of the transfer function, we can see that the impulse response is equal to k multiplied by omega n squared times t times e to the power of minus omega n t times dt. And then the step response ot, it can also be obtained by using the inverse Laplace transform of 1 over s times h squared by s. And here, this is actually the inverse Laplace transform of k over s minus k over s plus omega n minus k omega n over s plus omega n squared. Okay. Now we compare this case with the previous case. So here, what is the decay rate of the impulse response here? So here the decay rate is equal to omega n. Right? You can see that it is e to the power of minus omega n. So the decay rate is equal to omega n. Compared to the overdamped system, is it decaying faster or slower? Is it decaying faster or slower? Slower or faster? If it is faster, please raise up your hand. Oh, if it is faster, please raise up your hand. Yeah, it's correct. So it is actually decaying faster because, as I have mentioned before, in the overdamped system, ht will be dominated by the second term. So the second term, the decay rate of the second term is less than omega n, which means it is slower than omega n. Therefore, the critical damped system is the fastest, has the highest decay rate. So we can see that it decays faster than over damped systems. Of course, we must have the same omega n. If we have the same omega n, then it is faster than the overdamped system. So now we proceed to the underdamped system. For underdamped system, we have conjugate complex poles with damping ratio between 0 and 1. So when we see the poles have complex values, we will know that we will have both decay and oscillations, which is consistent with the phenomenon here. We can see the impulse response is decaying and oscillating. Right? So we have decay and oscillations. We have decay plus oscillations. And then here the transfer function is k omega n squared over s plus sigma squared plus omega d squared. If we do the inverse Laplace transform to this transfer function, we will obtain the impulse response, which is equal to k times omega n squared over omega d times exponential minus sigma t times sine omega dt times ut. And sigma here is equal to omega n times sigma, which is the natural frequency times the damping ratio. And then to calculate the step response function, we actually can also use this inverse Laplace transform of 1 over h delta s. So it is actually the inverse Laplace transform of k over s minus k times s plus sigma over s plus sigma squared plus omega d squared minus k times sigma over s plus sigma squared plus omega d squared. Now let's look at the last case of the second order systems. So in the last case, we have the damping ratio equal to 0. So in this case, we will have conjugate imaginary poles. Since we have conjugate imaginary poles, we know that the real part of the poles are equal to 0. If the real part of the poles are equal to 0, will there be any decay or not? No decay. So we will have no decay. Will there Now let's look at the last case of the second order systems. So in the last case, we have the density ratio equal to 0. So in this case, we will have conjugate imaginary poles. Since we have conjugate imaginary poles, we know that the real part of the poles are equal to 0. If the real part of the poles are equal to 0, will there be any decay or not? No decay. So we will have no decay. Will there be any oscillations or not? Yes, we have oscillations. So now we look at the impulse response here. We can see that, yes, there is no decay. Yeah, the peak value does not change. The peak value is always the same, no matter how t changes, and the oscillations. So it is oscillating all the way, right? So here we have the transfer function equal to capital K multiplied by omega n square over S square plus omega n square. And if we do the inverse Laplace transform, is equal to K multiplied by omega n times sine omega n t times ut. Okay, so we can see it is oscillating all the time. And then the step response of the system. Okay, so since this is the last case, so if you have some time, I will do this one for you. So here we have HTR.S given here. Therefore, the step function is equal to, step response is equal to the inverse Laplace transform of 1 over S multiplied by HTR.S, and it is equal to the inverse Laplace transform of 1 over S multiplied by K omega n square plus S square plus omega n square. And for this case, I'm going to assume that it is equal to the inverse Laplace transform of A over S plus BS plus C over S square plus omega n square. And how can I calculate A? A is equal to K omega n square over S square plus omega n square with S equal to 0. So A is equal to capital K, right? And how can I calculate B and C? So I can just reconstruct them. So I assume that here I have K over S plus BS plus C divided by S square plus omega n square, and it is equal to S multiplied by S square plus omega n square. And here I will have KS square plus K omega n square plus BS square plus CS. Therefore, it is equal to K plus B S square plus CS plus K omega n square divided by S multiplied by S square plus omega n square. And if I compare this expression with this expression here, I will find that K plus B is equal to 0, and C is also equal to 0. Therefore, I will have B equal to minus K, C equal to 0. Therefore, I will have OT equal to the inverse Laplace transform of K over S plus minus KS over S square plus omega n square. So this is actually equal to K times UT minus K times cosine omega n t times UT. Now, let's move on to the last example of today's lecture. So the response of a second order system to the input signal 2 delta t is 5 times e to the power of minus 3t times sine 4t. Derive the system transfer function, find the system poles, damping ratio, undamped natural frequency, and DC gain. Okay, so we know that xt is equal to 2 delta t, therefore the corresponding Laplace transform will be 2, and yt is equal to 5 times e to the power of minus 3 times sine 4t, therefore ytr that s will be equal to 20 over s square plus 6s plus 25. Okay, so in fact, when you look at this term, you can, so here you can always represent it in this here. So you will find that the system poles will be equal to minus 3 plus or minus j4. So for the impulse response, we will have both decay and oscillators, right? And then we are going to look at the damping ratio and the undamped natural frequency. So if we compare this transfer function with the standard form here, we will find that the natural frequency is equal to the term here, which is 25. Therefore, the natural frequency is equal to 5. And then if we compare this term with this term here, we will find 2 times the damping ratio times the natural frequency is equal to 6. Since we have omega n equal to 5, therefore we will have 6 times theta equal to 6. Therefore, theta will be equal to 0.6. And then the last one is the DC gain. DC gain is very simple. It is equal to the transfer function with s equal to 0. So if we set s, if we set s equal to 0 in this expression of HTR.S, then we will find the DC gain is equal to 10 over 25, which is equal to 0.4. And that's all for this example. So that's all for today's lecture. I will talk about the Bode diagram in next next class.
As we have learned in the last class, a body plot is an approximate visualization of the frequency response HTL.J omega of a system. As we have learned in it consists of straight line segments
So today we are going to learn the body diagrams. A body plot is an approximate visualizations of the frequency response, HTL-J omega of a system. So how can we get HTL-J omega? Once we have the transfer function of the system, which is denoted by HTL.S, and then we can replace S by J omega, then we will be able to get the frequency response of the system, which is HTL-J omega of the system. The body diagrams consist of straight line segments that are constructed based on the asymptotic properties of HTL-J omega. So a body plot is a combination of two plots. The first plot is called the magnitude plot, which is a plot of the magnitude of HTL-J omega in dB. It can be calculated as 20 times log 10 of magnitude of HTL-J omega dB. And the phase plot is a plot of the phase of HTL-J omega, and the unit of it is in degrees. The magnitude, when expressed in terms of dB, is frequently referred as the gain, since dB is a relative measure. For instance, if Vi and Vo are the input and output of a system, respectively, then we say that the system has a gain of 20 times log 10 of magnitude of Vo over Vi dB. Therefore, 20 times log 10 of Vo is the system gain measured with reference to a unit input, which means the magnitude of Vi is equal to 1. Okay. So in the body plots, the abscissa is logarithmically scaled. So the abscissa of the body diagrams is logarithmically scaled, and the body plots visualize only the positive frequency side of the frequency response. It is sufficient for real systems, since the magnitude of the frequency response is an even function and the phase is odd. So now we are going to learn how can we plot the body plots for a system. So we have three kinds of systems. The first kind of system is the system without integrator or differentiator. So in this case, the transfer function can be written as KDC multiplied by S over Z1 plus 1, S over Z2 plus 1 until S over Zn plus 1, divided by S over P1 plus 1, S over P2 plus 1 until S over Pn plus 1. So in this case, we do not have any differentiator or integrator in this system. And what is the DC gain of this system? So how can we calculate the DC gain of the system? If we want to calculate the DC gain of the system, we have to make S equal to 0, right? So when S is equal to 0, all the 0 factors and pole factors will be equal to 1. Therefore, the DC gain is equal to KDC here. KDC is the DC gain of the system. Here we have no differentiator or integrator in the system. Okay. Now we look at the nth order system with a differentiator. So here, what is a differentiator? A differentiator is denoted by KD times S. Here, KD is the gain of the differentiator, and the differentiator is multiplied by S over Z1 plus 1, S over Z2 plus 1, until S over Zn minus 1 plus 1, divided by S over P1 plus 1, S over P2 plus 1, until S over Pn plus 1. So how can we construct this system? This system consists of different subsystems. So the first subsystem is referred as the gain, since dB is a relative measure. For instance, if V of straight line segments, a combination of two plots. The first plot is called the magnitude plot, which is a plot of the magnitude of HTL-J omega in dB. It can be calculated as 20 times log 10 of magnitude of HTL-J omega dB. And the phase plot is a plot of the phase of HTL-J omega, and the unit of it is in degrees. The magnitude, when expressed in terms of dB, is frequently referred as the gain, since dB is a relative measure. For instance, if Vi and Vo are the input and output of a system, respectively, then we say that the system has a gain of 20 times log 10 of magnitude of Vo over Vi dB. Therefore, 20 times log 10 of Vo is the system gain measured with reference to a unit input, which means the magnitude of Vi is equal to 1. Okay. So in the body plots, the abscissa is logarithmically scaled. So the abscissa of the body diagrams is logarithmically scaled, and the body plots visualize only the positive frequency side of the frequency response. It is sufficient for real systems, since the magnitude of the frequency response is an even function and the phase is odd. So now we are going to learn how can we plot the body plots for a system. So we have three kinds of systems. The first kind of system is the system without integrator or differentiator. So in this case, the transfer function can be written as KDC multiplied by S over Z1 plus 1, S over Z2 plus 1 until S over Zm plus 1 divided by S over P1 plus 1, S over P2 plus 1 until S over Pn plus 1. So in this case, we do not have any differentiator or integrator in this system. And what is the DC gain of this system? So how can we calculate the DC gain of the system? If we want to calculate the DC gain of the system, we have to make S equal to 0, right? So when S is equal to 0, all the 0 factors and pole factors will be equal to 1. Therefore, the DC gain is equal to KDC here. KDC is the DC gain of the system. Here we have no differentiator or integrator in the system. Okay. Now we look at the nth order system with a differentiator. So here, what is a differentiator? A differentiator is denoted by KD times S. Here, KD is the gain of the differentiator. And the differentiator is multiplied by S over Z1 plus 1, S over Z2 plus 1, until S over Zm minus 1 plus 1, divided by S over P1 plus 1, S over P2 plus 1, until S over Pn plus 1. So how can we construct this system? This system consists of different subsystems. So the first subsystem is a differentiator, of which the transfer function is KDS. And the second subsystem is a zero factor, of which the transfer function is equal to S over Z1 plus 1. And then the second zero factor, which is S over Z2 plus 1, until we have the m minus 1 zero factor, which is S over Zm minus 1 plus 1. And then we are going to have the pole factors, which is 1 over S over P1 plus 1, and the second pole factor, which is 1 over S over P2 plus 1, until the last pole factor, which is 1 over S over Pn plus 1. So the system is a cascade of the subsystems here. Okay, and the gain of the differentiator is denoted by KD. So what is the DC gain of the system here? What is the DC gain of it? Since we have a differentiator here, when S is equal to 0, what is the value of H tilde S here? 0. Therefore, we see this DC gain of the system is equal to 0. Okay. So this is the nth order system with a differentiator. Now we look at the nth order system with an integrator. So in this case, the integrator is denoted by Ki divided by S. Therefore, the gain of the integrator is equal to Ki, and the transfer function of the whole system is equal to Ki divided by S multiplied by S over Z1 plus 1, S over Z2 plus 1, until S over Zm plus 1 divided by S over Z1 plus 1, until S over Pn minus 1 plus 1. So in this case, what is the DC gain of the system? When S is equal to 0, what is the value of H tilde S? Infinity. So in this case, the DC gain is H tilde 0, which is equal to infinity. Any questions so far? Okay, no questions. Okay, let's move on here. If we want to plot the body diagram of a specific systems, we need to learn the basic systems first, because all the systems can be constructed using the basic systems. Okay, so first we are going to learn the body plots of the basic systems here. The first basic system is called the DC gain. In this case, the transfer function is equal to a real constant, and this real constant is positive. So we have KDC larger than 0, H tilde S is equal to KDC, and KDC is real valued. The second basic system is a differentiator with gain equal to KD. Therefore, the transfer function is equal to kd multiplied by s. The third basic system is the integrator with gain equal to ki. In this case, the transfer function is equal to ki divided by s. And the fourth basic system is a zero factor with unity DC gain. In this case, the transfer function is equal to s divided by zm plus 1. When s is equal to 0, the transfer function is equal to 1. Therefore, it has the unity DC gain. And the fifth basic system is the pole factor, which is equal to 1 over s divided by pn plus 1. It also has the unity DC gain because when s is equal to 0, the transfer function is equal to 1. The last one is the second order factor with unity DC gain. It is equal to omega n squared divided by s squared plus 2 theta times omega n times s plus omega n squared. Here omega n is the undamped natural frequency and theta is the damping ratio. Okay. In this case, we will consider theta larger than or equal to 0, less than or equal to 1, which means we need to consider the undamped system, underdamped system, and critically damped system. Is that okay? Now let's move on to look at the body diagram of the basic systems one by one. First, let's look at the body plots for the DC gain. Okay, so I'm going to show you all the derivations on the right-hand side. Okay, so in this case, the transfer function is a constant which is larger than 0, and it is denoted by KDC. So we have the transfer function here. The next step is to replace S by j omega. So in the next step, we will have the frequency response equal to KDC, right? This is the frequency response of this basic system. So if we want to know the magnitude in dB, what should we do? We need to calculate the magnitude of HTL.j omega in dB, which is equal to 20 times log 10 of KDC. Okay. Since KDC is real and positive, so the magnitude of KDC is equal to itself. And then, what is the phase of it? The phase of HTL.j omega is equal to, what is the phase of a real and positive value? Is 0 or 90 degrees or 180 degrees? 0 degrees, right? So we can see that both the magnitude and the phase are independent of the frequency. They are both constant, right? So if you look at the magnitude plot, we can see that the magnitude plot is a straight line with slope equal to 0. So the magnitude is always equal to 20 times log 10 of KDC. It is a constant here. And then in the phase plot, we can see that the phase is always equal to 0 degrees. Okay? And it should be noted that in both the magnitude plot and the phase plot, this is called 1 decade. This is called 1 decade. Any questions so far? Okay, if there is no question, let's proceed to the next basic system. So the next basic system is a differentiator. So for the differentiator, the transfer function is equal to HTL.S, which is equal to KD multiplied by S, where KD is the gain of the differentiator. So if we want to know the frequency response of this basic system, we need to replace S with j omega, right? If we replace S with j omega, then HTL.j omega will be equal to KD multiplied by j omega. Do you still remember what is the exponential form of j? We've learned that in the complex plane, right? J is here. So we know that j is equal to e to the power of j 90 degrees. So in this case, it is equal to KD multiplied by omega multiplied by e to the power of j 90 degrees. Is that correct? Okay. So now here we assume that KD and omega are both larger than 0. Okay. Therefore, the magnitude of HTL.j omega in dB is equal to 20 times log 10 of KD multiplied by omega. This is because the magnitude of e to the power of 90 degrees is equal to 1. In fact, sometimes in the exams, we may play a lot of tricks. For example, we can write e to the power of j t squared plus 3t plus 90 degrees plus 4t squared. There is no need to care about the phase here. The magnitude will always be equal to 1. Because we do not care about the phase, we only care about the magnitude. It is always equal to 1. So when you see these kinds of expressions, you will know directly that the magnitude is equal to 1. Okay? So do not waste your time to calculate the magnitude here. Okay? So here we know that the magnitude will be equal to 20 times log 10 of KD times omega. So we can write it as 20 times log 10 KD plus 20 times log 10 of omega. Is that okay? So this is the magnitude in dB. We can see that the coefficient between log 10 of omega here, the coefficient here is plus 20. Therefore, the slope of the magnitude plot here is equal to plus 20 dB per decade. It means that the magnitude will increase 20 dB per decade. Okay. So in each decade, it will increase 20 dB. And from this expression here, what can we know? We know that it is a straight line with slope equal to plus 20 dB per decade. What else do we know? So here, when omega is equal to 1, what is the value of the magnitude in dB? When omega is equal to 1, the second term here will be equal to 0, right? Therefore, the magnitude in dB will be equal to the first term, which is 20 times log 10 of kd. Okay? And when omega is equal to 1 over kd, what is the magnitude in dB? When omega is equal to 1 over kd, what is the magnitude in dB? What is the magnitude in dB? So we will have 20 times log 10 of kd plus 20 times log 10 of 1 over kd, which is equal to 20 times log 10 of kd over kd. So it is equal to log 10 of 1 is equal to 0. So it is equal to 0 dB. Okay. So we can see that it will pass through 2 points here. One point is when omega is equal to 1, the corresponding magnitude is 20 times log 10 of kd. And when omega is equal to 1 over kd, the magnitude is equal to 0 dB. Okay, it will pass through these 2 points here. As for the phase of it, what is the phase of h tilde j omega? What is the phase of it? What is the phase of h tilde j omega here? 90 degrees. We can see that the phase is independent of the frequency. It is a constant. So in the phase plot, the phase is always equal to 90 degrees here. Any questions? Any questions? Okay, so if there is no question, let's move on. Now let's look at the body plots for integrator. So for integrator, the transfer function h tilde s is equal to ki over s. So in the first step, we are going to replace s with j omega to obtain the frequency response. Therefore, the frequency response h tilde j omega will be equal to ki divided by j omega. Okay. So 1 over j is equal to minus j, right? Minus j, and it is equal to e to the power of j times minus 90 degrees, because minus j should be here. So it is e to the power of minus 90 degrees. So we have e to the power of minus 90 degrees, so it is ki divided by omega times e to the power of minus j 90 degrees. Again, we assume that ki and omega are both positive. So in this case, the magnitude response in dB will be equal to 20 times log 10 of ki divided by omega. So it is equal to 20 times log 10 of ki minus 20 times log 10 of omega. Okay. So we can see that the coefficient between log 10 of omega here is minus 20. Therefore, the slope of this straight line here will be equal to minus 20 per decade. The slope here will be equal to the coefficient here, which is minus 20 dB per decade. Okay, now we look at the 2 points on the straight line. So for the first point, let's say if omega is equal to 1, what will be the magnitude? When omega is equal to 1, what is the magnitude of it? It's 20 times log 10 of Ki. And when omega is equal to Ki, what is the magnitude in dB? When omega is equal to Ki, the first term here will be equal to the second here. So the first term minus the second term will be equal to 0. So we will have 0 dB. So it means that this straight line will pass through 2 points. The first point is 20 times log 10 of Ki. The second point is Ki, 0 dB. How about the phase of the frequency response? What is the phase of the frequency response? What is the phase of it? Divided by Zm plus 1. And here Zm is positive. So in the first step, we are going to replace S Any questions so far? There is no question. Let's proceed to the next basic system. So the next basic system is the zero factor. So for the zero factor, the transfer function htl.s is equal to s divided by zm plus 1. And here zm is positive. So in the first step, we are going to replace s with j omega in order to obtain the frequency response. So in this case, the frequency response htl.j omega will be equal to j omega divided by zm plus 1. If we want to calculate the actual magnitude response and the actual phase response, what should we do? So let's say we do not do any approximations first. Let's calculate the actual magnitude response and the actual phase response. So if we do not do any approximations, then the magnitude of the frequency response in dB should be equal to 20 times log 10 of what? What is the magnitude of this term? Yeah. What is the magnitude of it? The magnitude of it is omega divided by Zm squared plus 1 squared. Right? It's the magnitude of it. And then the phase of it is, what is the phase of it? It is arctangent omega over Zm divided by 1. Are you able to plot the magnitude response and the phase response based on these two equations? Maybe yes, but it's too time consuming. So instead of using these two equations, we are going to make some approximations. So let's consider the case when omega is much less than Zm. So when omega is much less than Zm, what will happen to the frequency response here? When omega is much less than Zn, it means that the magnitude of the first term will be much less than 1, right? The magnitude of the first term will be much less than 1, so it means that the first term here can be neglected. So the frequency response in this case is approximately equal to 1. So when omega is much less than Zm, it means that the magnitude of the first term is much less than 1, so it can be neglected. Therefore, the frequency response is approximately equal to 1. So what is the magnitude in dB? 1 dB, 0 dB, 10 dB, 20 dB, 0 dB, right? So it is equal to 0 dB. And what is the phase of it? What is the phase of 1? 0 degrees. Okay, so we can see that in the magnitude plot, when the frequency is less than Zm, we have the magnitude equal to 0 dB. And in the phase plot, when the frequency is less than Zm divided by 10, which means the frequency is much less than Zm, the phase is equal to 0 degrees. Okay. Now let's consider the second case. What will happen if omega is much larger than Zm? So if omega is much larger than Zn, it means that the magnitude of the first term will be much larger than 1. When omega is much larger than Zm, the magnitude of the first term will be much larger than 1. In this case, the frequency response can be approximated as j omega divided by Zm. Is it correct? So in this case, what is the magnitude in dB? The magnitude in dB will be equal to 20 times log 10 of omega divided by Zm. Here we assume that omega and Zm are both larger than 0. So we can write it as 20 times log 10 of omega minus 20 times log 10 of Zm. Since log 10 of omega is multiplied by 20 here, therefore, when frequency is larger than Zm, the slope here is plus 20 dB per decade. And when omega is equal to Zm, the magnitude here is equal to 0 dB. Now we look at the phase. The phase of HTL.J omega. So here, HTL.J omega is approximated as J omega over Zm. What is the phase of J here? What is the phase of J? 90 degrees. Okay. Therefore, when the frequency is much larger than Zm, which means the frequency is larger than 10 times Zm, the phase will be equal to 90 degrees here. And in between, when the frequency is between Zm over 10 and 10 Zm, we can just connect these 2 points. Now I have a question for you. We know that the body plots is the approximate visualization of the frequency response, right? What if I want to know the actual response at this point? So when the frequency is equal to Zm, what is the actual response here? What is the magnitude of the actual response here? When omega is equal to Zm, what is the actual magnitude response here? What is the value here? Obviously, from this graph, it is between 0 dB and 10 dB. You can make a guess. Okay. Usually, I will guess it is equal to 3 dB. Okay. So let's look at why. So this is the actual magnitude response. We can see that when omega is equal to Zm, here omega divided by Zm will be equal to 1. So we will have square root of 2, right? So here, for this point, we will have the magnitude equal to 20 times log 10 of square root of Zm divided by Zm squared plus 1, which is equal to 20 times log 10 of square root of 2, and it is actually equal to 3 dB. So this is the actual magnitude response here. Any questions so far? Yes, always take. Any questions? Any questions? So it's the 0 factor. Now, if there is no question, let's proceed to look at the pole factor. So for the pole factor, the transfer function is equal to 1 divided by s over Pn plus 1. In the first step, we are going to replace s by j omega. Then the frequency response, HTL.J omega, will be equal to 1 divided by j omega over Pn plus 1. So if we do not do any approximations to this frequency response, what is the magnitude of it in dB? The magnitude will be equal to 1 divided by square root of omega over Pn squared plus 1 squared. Right? This is the actual magnitude response. Is that correct? This is the actual magnitude response. How about the actual phase response? It is equal to the phase of 1 minus the phase of the denominator. So the phase of 1 is 0, right? And the phase of the denominator is arctangent omega over Pn divided by 1. So it is arctangent omega over Pn divided by 1. Here it has a minus sign. But based on these two equations, we may be able to plot the magnitude response or phase response, but it is quite time consuming. Therefore, we are going to make some approximations. So in the first case, let us assume that omega is much less than Pn. When omega is much less than Pn, what will be the frequency response here? When omega is much less than Pn, it means that the magnitude of the first term in the denominator will be much less than 1. So the denominator can be approximated as 1. So the frequency response is approximately equal to 1 here. So the magnitude of the frequency response in dB will be equal to 0 dB, and the phase of the magnitude response will be equal to 0 degrees. So we can see in the magnitude plot, when the frequency is less than Pn, the magnitude is equal to 0 dB, and in the phase plot, when frequency is less than Pn over 10, the phase is equal to 0 degrees. Now we discuss about the second case, when omega is much larger than Pn. In this case, the frequency response can be approximated as 1 divided by j omega over Pn, which is minus j times Pn over omega. Is that correct? So what is the exponential form of minus j? What is the exponential form of minus j? E to the power of j, and then 90 degrees or minus 90 degrees, minus 90 degrees, multiplied by Pn over omega. Therefore, the corresponding magnitude in dB will be equal to 20 times log 10 of Pn divided by omega. So it is equal to 20 times log 10 of Pn minus 20 times log 10 of omega. We can see that the coefficient between log 10 of omega is minus 20. Therefore, the slope here is minus 20 dB per decade. When frequency is larger than Pn, the slope of the straight line will be equal to minus 20 dB per decade. And how about the phase? How about the phase? What is the phase of the frequency response when omega is much larger than Pn? The phase is equal to minus 90 degrees, right? So it is equal to minus 90 degrees. When omega is larger than 10 times Pn, the phase is equal to minus 90 degrees. So now I have a question for you. What is the actual magnitude response here at omega equal to Pn? What is the value here? Minus 3 dB, right? This is because we have the magnitude equal to 20 times log 10 of 1 divided by square root of Pn over Pn square plus 1 square, which is minus 3 dB. Okay? Therefore, the actual magnitude response at omega equal to Pn is equal to minus 3 dB. Any questions so far? Any questions? So if there is no question, let's look at the last basic system, which is a second order factor. So for the second order factor, we have theta larger than or equal to 0, less than or equal to 1. When theta is equal to 0, what kind of system is it? Is it undamped, underdamped, or critically damped? When theta is 0, are the poles imaginary or real? Not real. Should be imaginary, right? When theta is equal to 0, then the poles will be purely imaginary. So if it is purely imaginary, is it undamped? Should be undamped. So when theta is equal to 1, what will be the poles? The poles will be, when theta is equal to 1, what are the poles here? The poles are equal to, when theta is equal to 1, we will have s squared plus 2 omega ns plus omega n squared, which is s plus omega n squared. It means that the poles is equal to minus omega n, right? And minus omega n, so to 0, which means that the poles will be equal to plus or minus j omega n. Oh, sorry, here. When theta is equal to 1, the poles will be purely real, so it will decay without any oscillations. When theta is equal to 0, since the poles are purely imaginary, so it will oscillate without any decay, right? So this case is called critically damped. This case is called undamped. Okay. So now let's proceed to look at the transfer function. So in this case, the transfer function htl.s will be equal to omega n squared divided by s squared plus 2 theta omega ns plus omega n squared. So in the first step, we are going to replace s by j omega. Then the frequency response will be equal to htl.j omega, which is omega n squared divided by minus omega squared plus 2j theta omega n omega plus omega n squared. And then let's calculate the actual magnitude response in dB. So what is the actual magnitude response in dB? It is equal to 20 times log 10 of omega n squared divided by square root of omega n squared minus omega squared square plus 2 theta omega n omega square. Is it correct? How about the phase of htl j omega? The phase of it is equal to the phase of the numerator minus the phase of the denominator. What is the phase of the numerator here? The phase of omega n squared is 0, right? So we have 0 divided by 0 minus the phase of the denominator, which is arctangent 2 theta omega n omega divided by omega n squared minus omega squared. So this is the actual phase response. Is it correct? So instead of using these two equations here, we are going to make some approximations to the magnitude response and phase response. First, let us assume that omega is much less than omega n. If omega is much less than omega n, what do we have for the frequency response? If omega is much less than omega n, it means that the first term in the denominator and the second term in the denominator will be much less than the third term, right? It means that we can neglect the first term and the second term in the denominator. Is that correct? When omega is much less than omega n, it means that the magnitude of the first term and the magnitude of the second term will be much less than the magnitude of the third term, because omega is much. Does it make sense? Neglected. What is the phase of 1? Phase of 1 is equal to 0 degrees, right? When the frequency is less than omega n, the magnitude in dB is equal to 0 dB. And when the frequency is less than 0.1 omega n, the phase is equal to 0 degrees. Now we look at the second case, when omega is much larger than omega n. Then in this case, the frequency response will be approximately equal to, so when omega is much larger than omega n, we can see that the first term in the denominator, the magnitude of the first term will be much larger than the magnitude of the second term, and it will also be much larger than the magnitude of the third term. So in this case, the second term and the third term in the denominator can be neglected. So in this case, the frequency response will be equal to omega n squared divided by minus omega squared. So here we will have minus 1. For minus 1, it is actually equal to e to the power of plus or minus j 180 degrees. But here we choose the phase to be negative. So here we will use minus 1 equal to e to the power of minus j 180 degrees. So we can write it as omega n squared divided by omega squared multiplied by e to the power of minus j 180 degrees. Therefore, the magnitude of HTL dot j omega in dB will be equal to 20 times log 10 of omega n squared divided by omega squared. And it is equal to 40 times log 10 of omega n minus 40 times log 10 of omega. Since log 10 of omega n is multiplied by minus 40 here, therefore we can see that when the frequency is larger than omega n, the slope of the straight line here will be minus 40 dB per decade. The coefficient here is corresponding to the slope of the straight line here. As for the phase of HTL dot j omega, we can see that the phase of this expression here, it is a constant, which is always equal to minus 180 degrees. Therefore, when the frequency is larger than 10 times omega n, the phase will be equal to minus 180 degrees. It's just a convention. Now I have a question here for you. So in this case, we said that we consider the Bode plots for the second order factor where we restrict the value of theta to be larger than or equal to 0, less than or equal to 1. How about the case when theta is larger than 1? Why don't we consider the case when theta is larger than 1? When theta is larger than 1, what will happen? Okay, so we look at the polynomial here. So the polynomial of the denominator, when theta is larger than 1, so we need to solve for the pose, which is s squared plus 2 theta omega ns plus omega n squared equal to 0. So the pose will be equal to when theta is larger than 1, the pose will be equal to this value. What can we see here? We can see that we have two real and distinct poles, right? We will have two real and distinct poles. So if we have two real and distinct poles, it can be regarded as the pole factors here. So it has already been discussed in the pole factors here. So we do not need to consider the case when theta is larger than 1. Okay. So now we have finished all the basic systems. Now we proceed to look at the asymptotic behavior of the body plots. Okay. So for the body plots, for the asymptotic behavior of the body plots, we need to discuss the high frequency case and low frequency case. First, let's look at the low frequency case. As we have studied 5 basic systems, the first one is KDC. The second one is KD multiplied by S. The third one is KI multiplied by 1 over S. The fourth one is 1 divided by S divided by. Okay. So now we look at all the 6 cases. So for the first one, the frequency response will still be KDC. The second one, the frequency response will be KD divided as for the last omega n square. Okay. So now we have written all the 6 subsystems. We want to look at the low frequency case. So we need to discuss the slope as well as the phase. The slope is dB per decade, and the phase is in degrees. Okay, so we consider the low frequency case for the DC gain first. For the DC gain, what is the slope of it? What is the slope of it? Slope of the DC gain is equal to, does it change with time? Or does it change with frequency? No. So the slope is equal to 0, right? Differentiate. Slope of it, the first term can be neglected. So it's like the DC gain. When the frequency is very low, it's also like the DC gain, right? When the frequency and 0, and the phase will be equal to 0 degrees. So in the low frequency case, what do we need to consider? We only need to consider the differentiator and the integrator. Is it correct? So here, in the low frequency case, the slope will be equal to the number of integrators, which is case 3, minus the number of differentiators, which is case 2, multiplied by minus 20 dB per decade. Okay. And the phase will be equal to the number of integrators minus the number of differentiators multiplied by minus 90 degrees. And these two equations are summarized on the slide here. So here, in the low frequency case, the phase is equal to the number of integrators, which is the number of case 3 minus the number of differentiators, which is the number of case 2, multiplied by minus 90 degrees. And in the low frequency case, the phase is equal to the number of integrators, which is the number of case 3, minus the number of differentiators, which is the number of case 2, multiplied by minus 20 dB per decade. So now let's proceed to look at the high frequency case. So for the high frequency case, we also need to consider these 6 basic systems. First case is KDC, which is equal to KDC in the frequency response. Second case is KD multiplied by S, which is equal to
KD multiplied by J omega in the frequency response. The third case is Ki multiplied by 1 over S, which is Ki multiplied by 1 over J omega in the frequency response. And the fourth case is S over Zm plus 1, which is J omega divided by Zm plus 1 in the frequency response. And the fifth case will be 1 divided by S over Pn plus 1, which is 1 divided by J omega over Pn plus 1 in the frequency response. And the last case is omega n squared divided by S squared plus 2 theta omega n S plus omega n squared, which is omega n squared divided by minus omega squared plus 2j theta omega n omega plus omega n squared in the frequency response. Okay, so still we need to consider the slope in dB per decade and the phase in degrees. So in the high frequency case, for the DC gain, what is the slope of it? What is the slope of the DC gain here? 0. And what is the phase of it? 0 degrees. And in the second case, we have the differentiator. So for the differentiator, what is the slope of it? The slope of it is equal to plus 20 dB per decade. How about the phase of it? 90 degrees. Then for the integrator, what is the slope of it? Minus 20 dB per decade. How about the phase of it? Minus 90 degrees. And for the fourth case, when the frequency is very high, it means that the second term can be neglected. So it can be approximated as J omega over Zm. If it is approximated as J omega over Zm, what is the slope of it? The slope of it is plus 20 dB per decade. How about the phase of it? The phase of J is 90 degrees. And in the fifth case, it is the pole factor. When omega is much larger than Pn, the denominator can be approximated as J omega over Pn. So what will be the slope of this frequency response? The slope of it is equal to minus 20 dB per decade, and the phase of it is minus 90 degrees. And then for the last case, when omega is much larger than omega n, the denominator can be approximated by the first term here, so that the frequency response can be approximated as omega n squared divided by minus omega squared. So the slope of it is equal to minus 40, and the phase of it is equal to minus 180 degrees. So in this case, we need to consider 5 cases from case 2 to case 6. So the slope of the system will be equal to the number of case 3 plus the number of case 5 plus 2 multiplied by the number of case 6 minus the number of case 2 plus the number of case 4. And it is multiplied by minus 20 dB per decade. And in this case, the summation of case 3 plus case 5 plus 2 times case 6, it is called the number of poles. And the number of case 2 plus the number of case 4, it is called the number of zeros. As for the phase, we will have the number of case 3 plus the number of case 5 plus 2 multiplied by the case 6 minus the number of case 2 plus the number of case 4 multiplied by minus 90 degrees. Again, this is called the number of poles. This is called the number of zeros. So now let's move on to look at some examples here. So in example 8-1, we have the cascade of two distinct first-order systems. In this case, so now let's move on to look at some examples here. So in example 8-1, we have the cascade of two distinct first-order systems. In this case, the transfer function is equal to 10 divided by 10s plus 1 times s plus 1. So in this case, h tilde s is equal to the multiplication of three transfer functions, which is h1 tilde s, h2 tilde s, and h3 tilde s. Here h1 tilde s is equal to 10, h2 tilde s is equal to 1 divided by s over 0.1 plus 1, h3 tilde s is equal to 1 over s plus 1. So in the S domain, we have h tilde s equal to h1 tilde s multiplied by h2 tilde s multiplied by h3 tilde s. So if we calculate the dB value of h tilde, magnitude of h tilde s, it will be equal to the magnitude of h1 tilde s in dB plus the magnitude of h2 tilde s in dB plus the magnitude of h3 tilde s in dB. So first, we are going to plot the magnitude response of the three subsystems, and then we can sum them up. Okay. So for the first subsystem, it is a DC gain, which is equal to 10. So for 10, the corresponding dB value will be equal to 20 times log 10 of 10, which is equal to 20 dB. So the corresponding magnitude response will be a constant, which is always equal to 20 dB. Okay, maybe I will use the red color to denote it. So here, this is the magnitude response of the first subsystem. And now we look at the second subsystem. The second subsystem is a pole factor. So when the frequency is very low, the pole factor is like the DC gain. And when the frequency is very high, the pole factor is like the integrator, right? So here, the slope change will happen at omega equal to 0.1. So for the second subsystem, I will use the green color. So initially, it is equal to 0 dB, which is here. And the slope change will happen at omega equal to 0.1. After that, the slope of the straight line will be equal to minus 20 dB per decade, which is like the integrator. Now we look at the third one. So for the third one, I will use this color here. h3 tilde s is equal to 1 over s plus 1, we can see that for this one, when the frequency is very low, it's like the DC gain, which is equal to 0 dB. And when the frequency is very high, it's like the integrator, which is 1 divided by s. So in this case, the slope change will happen at omega equal to 1, which is here. So the magnitude response of h3 tilde s is represented by this plot here. Now the only thing we need to do is to sum them up. So we are going to divide the frequency domain into different segments such that within each segment we only have straight lines. Right? So to do the summation, we are going to divide the frequency domain into different segments. And then do the summation. In this way, we are going to obtain the magnitude response of h tilde s. Now we look at the phase response. So for the phase response, we first look at the phase response of h tilde 1s. So what is the phase of 10? The phase of 10 is equal to 0 degrees. So here it is represented by a straight line in red. So the phase response of h1 tilde s is represented by this red line here. Now we look at the second transfer function, h2 tilde s, very low. It is like the DC gain, of which the phase is equal to 0 degrees. And when the frequency is very high, it is like the integrator. So the phase of the integrator will be equal to minus 90 degrees, which is here. Right? So when the frequency is less than 0.1 times 0.1, the phase will be equal to 0 degrees. And when the frequency is larger than 10 times 0.1, the phase will be equal to minus 90 degrees. And in between, we can connect these 2 points here. Now we proceed to look at the third transfer function, h3 tilde s, which is equal to 1 over s plus 1. So from this transfer function, we know that when the frequency is very low, it is like the DC gain. So the phase of the DC gain here is equal to 0 degrees, which is shown here. And when the frequency is very high, it is like the integrator. The phase of the integrator will be equal to minus 90 degrees, which is here. And in between, we can connect these 2 points. In order to obtain the phase response of h tilde s, we can do the summation of these 3 phase plots. So we are going to partition the time domain into different segments such that within each segment, we only have straight lines. So we are going to do the partition here. 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 And also here. And then we can do the summation to obtain the phase plot of h tilde s. Any questions? If there is no question, let's proceed to look at the second example here. So in example 8-2, we have the cascade of one integrator and one first order system. So here the transfer function is equal to 1 divided by s times 0.1 s plus 1. So it can be regarded as the multiplication of 1 divided by s multiplied by 1 divided by s over 10 plus 1. So first, let's look at 1 divided by s. 1 divided by s is an integrator. So for this integrator, the slope of the magnitude response will be equal to minus 20
minus 20 dB per decade, right? So here, let's use the red color here. The magnitude plot of this integrator is plotted using the red color. And then for the phase of it, the phase of the integrator will always be equal to minus 90 degrees, which is shown here. And then for the second subsystem, we are going to use the green color. So for the pole factor here, when the frequency is very low, it is like the DC gain. Therefore, initially, the magnitude of it will be equal to 0 dB, which is shown here. And then the slope change will happen at omega equal to 10. After that, it is like an integrator, which means the slope will be equal to minus 20 dB per decade. As for the phase plot of the second subsystem, initially when the frequency is very low, it is like the DC gain. So the phase of the DC gain is equal to 0 degrees. And when the frequency is very high, it is like an integrator. The phase of the integrator is equal to minus 90 degrees. And in between, we can connect these 2 points here. So to obtain the magnitude plot of HTL.S and the phase plot of HTL.S, we can just do the summation, which means we can partition the frequency domain into different segments and do the summation in each segment. Now we proceed to look at the third example, 8-3. In this case, the system is a cascade of one differentiator and one second order system. HTL.S is equal to 100s divided by s squared plus 10s plus 100. So in this case, H1TL.S is equal to s, and H2TL.S is equal to 100 divided by s squared plus 10s plus 100. Okay, so for the differentiator, the slope of the magnitude plot will be equal to plus 20 dB per decade. So I'm going to use the green color here. So for H1TL.S, the magnitude plot is plotted in the green color, which is shown here. And the phase of it is always equal to 90 degrees, which is also plotted using the green color here. And then for H2TL.S, when the frequency is very low, it is like the DC gain, of which the magnitude is equal to 0 dB. And the slope change will happen at omega n. So here we have this expression is actually omega n squared divided by s squared plus 2 zeta omega n s plus omega n squared. So we can see that omega n squared is equal to 100. Therefore, the slope change will happen at omega equal to 10, which is here. And after that, it is like the double integrator, right? After that, it is like a double integrator, of which the slope of the magnitude plot is equal to minus 40 dB per decade. Here is minus 40 dB per decade. And in the phase plot, initially it is like the DC gain. Therefore, the phase is equal to 0 degrees, which is shown here. And when the frequency is very high, the phase is equal to the phase of double integrator, which is minus 180 degrees. And in between, we can connect these 2 points. Okay. And in order to obtain the magnitude plots and the phase plots of HTL.S, we can do the summation segment by segment. So we are going to partition the frequency domain into different segments. Here, here, and here. And then do the summation. Any questions about these 3 examples? No. Okay. So now we can proceed to look at one example here. The Bode plot for several values of theta is shown in figure 8-1 for the LT. System of which the transfer function is given by HTL.S equal to 10 times omega n squared divided by s squared plus 2 zeta omega ns plus omega n squared. So we can see that in these 3 cases, when theta is equal to 0.1 and when theta is equal to 0.3, we have a resonant peak here near the frequency equal to omega n. So it should be noted that the frequency response has a hump around omega equal to omega n. This hump is more pronounced when theta is small and disappears when theta rises above a certain value. This hump is associated with the phenomenon of resonance. And this hump is called the resonant peak. The frequency is called the resonance frequency. Okay, so we want to find the position of the resonant peak. What should we do? First, we calculate the magnitude of the frequency response. So the magnitude of the frequency response here, maybe we can do it step by step. Okay, so here, first we have the transfer function equal to 10 times omega n squared divided by s squared plus 2 zeta omega n times s plus omega n squared. And then to obtain the frequency response, we can replace s by j omega. If we replace s by j omega, we will have the frequency response HTL by j omega equal to 10 omega n squared divided by minus omega squared plus 2 zeta omega n times j omega plus omega n squared. And it is equal to 10 omega n squared divided by minus omega squared plus omega n squared plus j times 2 zeta omega n times omega. Therefore, the corresponding magnitude of HTL by j omega will be equal to 10 multiplied by omega n squared divided by the square root of minus omega squared plus omega n squared plus 2 zeta omega n multiplied by omega squared. And yeah, it's like this. And if we want to find the maximum value of this magnitude, it is equivalent to find the minimum value of the denominator. So we want to find the minimum point of the denominator. What should we do? We are going to calculate the derivative of the denominator with respect to omega. So the denominator is equal to minus omega square plus omega n square square plus 2 theta omega n omega square. And we make it equal to 0. Okay. And what do we have for this derivative? We will have 1 over 2 multiplied by, in the denominator, we have the square root of minus omega square plus omega n square square plus 2 theta omega n times omega square. And in the numerator, what do we have? We will have 2 multiplied by minus omega square plus omega n square multiplied by minus 2 omega plus 2 times 2 theta omega n omega multiplied by 2 theta omega n. And this is equal to 0. So in order to make this expression equal to 0, we need to have this numerator equal to 0. Right? This numerator will be equal to 0, so that we will have, we can remove 2. So we will have minus omega square plus omega n square times minus 2 omega plus 2 theta omega n times omega multiplied by 2 theta omega n equal to 0. Omega n. It is equivalent to find the minimum value of the denominator. So we want to find the minimum point of the denominator. Minus omega square plus omega n square square plus 2 theta omega n multiplied by omega square. And yeah, it's like this. And if we want to find the maximum value of this magnitude, it is equivalent to find the minimum value of the denominator. So we want to find the minimum point of the denominator. What should we do? We are going to calculate the derivative of the denominator. We need to have this numerator equal to 0. Right? This numerator will be equal to 0, so that we will have, we can remove 2. So we will have minus omega square. And then omega is a common factor. So we will have omega times minus 2 multiplied by omega n square minus omega square minus 2 theta square omega n square equal to 0. So it is equal to minus 2 omega multiplied by omega n square times 1 minus 2 theta square minus omega square equal to 0. So we will have 3 roots for omega. The first root is omega equal to 0. The second and the third root is omega equal to plus or minus omega n times square root of 1 minus 2 theta square. Since we need to have omega larger than 0, therefore we will have the resonant frequency equal to omega n multiplied by 1 minus 2 theta square. This is the resonant frequency of the system. So after we get this resonant frequency, we are able to get the resonant peak by substituting omega equal to the resonant frequency here. And we find that the resonant peak is equal to k divided by 2 theta times square root of 1 minus theta square. So from these two expressions, what can we get? We find 2 theta times square root of 1 minus theta square. So from these two expressions, what can we get? We find that the resonance will only happen when theta square is less than 1 over 2, because the resonant frequency will be real only when theta square is less than 1 over 2. Okay. There is no resonance if theta is larger than or equal to 1 over 2. So what does it mean by saying that theta is less than 1 over 2? It means that the system is closer to the undamped system. It is closer to the undamped system, then the resonance will happen. So when theta tends to 0, when theta is equal to 0, it means undamped, right? In the undamped case, the resonant frequency will tend to the natural frequency, and the resonant peak will tend to infinity. So for the undamped system, it means that the impulse response will oscillate all the way without any decay. So there will be a resonant peak at omega equal to omega n, and the resonant peak is equal to infinity. So now let's look at the example here. So we can look at this case. When theta is equal to 0, it is corresponding to the undamped system. So the resonant peak will be equal to infinity. And when theta is equal to square root of 1 over 2, then it is corresponding to the resonance threshold, which means when theta is less than this value, we will have a resonance. And when theta is equal to 1, it is a critically damped system, which means there is no resonance. And when theta is equal to 0.3, we have a resonance here. And it is corresponding to the underdamped system. Okay, so now let's look at the example here. So we can look at this case. When theta is equal to 0, it is corresponding to the undamped system. So the resonant peak will be equal to infinity. And when theta is equal to square root of 1 over 2, then it is corresponding to the resonance threshold, which means when theta is less than this value, we will have a resonance. And when theta is equal to 1, it is a critically damped system, which means there is no resonance. Then it is correct. Now let's look at the example here. So we can look at this case. When theta is equal to 0, it is corresponding to the undamped system. So the resonant peak will be equal to infinity. And when theta is equal to square root of 1 over 2, then it is corresponding to the resonance threshold, which means when theta is less than this value, we will have a resonance. And when theta is equal to 1, it is a critically damped system, which means there is no resonance.